Hey, Honors Physics, Mr. Hausman here. We're going to take a look at number 2 on page 6, horizontal projectiles. So we started this one the other day. What we're talking about here is we have a situation where a cherry pit is moving along at a horizontal speed of 18 meters per second. And why is that relevant? Well, because if that object is moving along at 18 meters per second in a car and it's dropped, it's going to turn into a projectile that moves forward at 18 meters per second the entire time it's in the air. And that consistent horizontal velocity we call Vx. So the Vx is 18 meters per second. That's quite fast. Now, we don't know how far it lands ahead of the car. We don't know the delta x. That's called the range. And the range is actually the unknown. How far horizontally from the dropping point will the pit hit the ground? We don't know that. And you might get stuck because you're like, well, we also don't know time. So this is not a simple problem, just like we would have done in the past with horizontal motion. You know 2 variables, and you solve for a third. Instead, we're going to have to look at the vertical data. So what do we know about the vertical motion of a projectile? Well, if it is moving horizontal, completely horizontal, not up, not down, then its vertical velocity when it starts is 0. And we do not know the velocity when it hits the ground. We'll just leave that blank. But we do know that the acceleration is free fall. It's the gravitational acceleration of our planet. And we know that the delta y is -1 meter. Now, it doesn't say that, but you have to interpret that if it starts 1 meter above the ground, and then by the time it hits the ground below the car window, it is now -1 meter. That's important. It will not work out mathematically if you don't do that. And you might say, well, there's no way to continue this. But in fact, what's going on is that if you notice you have 3 given in the vertical side, then what you can do is you can use your kinematics formula to solve for t. Why t? Well, the reason is because time is in both sides. It's the same time. That is to say, the time to land out here is the same as the time to drop. So if we did a free fall drop problem and found the time to drop here, it's the same as the time it takes to land here. We did a demo in class and the marbles landed at the same time. I wasn't trying to, when we did that, emphasize that it's a lot different, but in many times when we've used high-speed cameras in the past, it's off by a little tiny bit, like a tenth or even less of a second. But sometimes it's not exactly the same due to air resistance. So let's go ahead and let's set up and think about what formula would we use to solve for t as our unknown. And I bet you can take out your equation card, do that now. And you're going to notice that you have a formula, delta y equals VIT plus 1/2 AT squared. It has delta y in it, it has v in it, v initial, it has t, and it has a. And your gut feeling may say that's quadratic if I'm solving for t. And in this case, because the v initial is 0, it's a little bit simpler. We just plug in -1 meter, v initial is 0, so that whole term cancels out. Half of -9.8 is -4.9, t squared. Divide both sides by -4.9, and t comes out to be, right, we have to first divide, and then we're going to square root. I'm going to do all those steps at the same time. So let's do that. Square root of 1.0 divided by 4.9. The 2 negatives cancel out. And you get a time of 0.452 seconds. Do we need all those decimals? Maybe we could stop at 0.45 because that's what the given had. But the reason why we carry another is that's not the final step. That's just step 1. Now we can use that 0.45 seconds, and the only formula that we have available to us for non-accelerated motion is velocity equals delta x over t. And now we can plug in our 18 meters per second equals a range, a delta x we do not know, but the time is 0.45 seconds. And when you cross multiply, you get 8 8.1 meters. Check that out, see if you get it. And that is how far the pit lands in front of its starting position, how far out. And the car probably kept up with it. So Lisa would look out the window, look at the cherry pit, think she's dropping it straight down. But anyone who's outside the car would see it move forward at 8.1 meters. Okay, let's do the bottom of 6. So the bottom of 6 is another similar scenario, but instead of Lisa Simpson, it's the Hulk, the big green Hulk. So he tosses a piece of granite. And I don't know how you throw things. Sometimes you throw it up at an angle. But in this case, we find out that he really pushes it forward. There's a horizontal velocity, and it's a piece of granite, so it's not moving that fast. Well, it is the Hulk. And it moves forward, curves, and in this case, he's throwing it out from the ledge of a cliff. What that really does is it allows us to have some drop, and then there's water at the bottom. And the question is, how far out? This is another exactly the same range problem. So let's go ahead and see how that works. We've got a Vx of 3.0 meters per second. We have a range we don't know. We have a time we do not know. We have a V initial of, say it with me, 0. The starting height for all projectiles that are launched horizontally is 0. You can count on that if it is a horizontal launch, if it's thrown sideways. Let's see, what else do we know? We know the acceleration is negative 9.8, always on planet Earth. And the delta y, I believe we know, is negative 10 meters. It's dropped 10 meters. And what's going to be our unknown? We're going to solve for t on the vertical. And the question is, do we always go from y to x? And the answer is no. If you knew 2 pieces of data on the horizontal side, then you might find yourself going the other direction. And I bet a lot of us can kind of foresee that happening. What you really need to have is your equation card out in front of you, and we're going to learn with a little bit of practice how to use any set of given to find any unknown or unknowns. So let's set this up. What did we do last time? We used delta y equals VIT plus 1/2 AT squared. We have the ease of canceling out VI because it's 0. And then we have negative 10 meters equals negative 4.9 T squared. This is going to become quite easy for you in a matter of maybe 2 practice problems. So let's go ahead and do that. Let's take the square root of 10 divided by 4.9. Now, if you notice that one of those is positive and you're therefore taking the square root of a negative, then what you've probably forgotten is you've forgotten one of these negatives. Projectiles always, that are thrown horizontal, always have negative displacements because they're curving downward. So you can't take the square root of a negative number, so those double negatives have to be there. And the answer I get is 1.43 seconds. I'm keeping an extra sig fig, an extra digit, because that's just step 1. Let's go ahead now and use our horizontal motion. We've got Vx in the horizontal equals our range over our time. How fast it's going, we know is 3 meters per second sideways. We don't know the range, and we know it takes 1.43 seconds. So the velocity is slower than the cherry pit, but the time is greater. Let's see how this works out. What is 3 times 1.43? That's me just mistyping it on my calculator. Sorry for the delay. And I get 4.3 meters. Okay. These may seem pretty basic. They will get more challenging when we have multiple unknowns or when we have to be flexible and we have to go the other direction, time from the X to the Y. But so far, that's a good start. I'd like you to try the next few problems for a homework assignment.